Algebra 2, 5.9, write polynomial functions and models. So, for example 1, write a cubic function whose graph is shown. So, we have our three x-intercepts here, so we can write this fairly easily in factored form. So we have x minus 3, so remember it's always x minus whatever our 0 is, x minus 1, and x minus a negative 4, which is the same as x plus 4. So now we have to figure out if we have a number here multiplied by it at the beginning here. So if we put 0 in here, we get 0 minus 3 is negative 3. 0 minus 1 is negative 1. 0 plus 4 is 4. If I multiply those together, I get a positive 12. Well, we want a negative 6 because that is our y-intercept. So, in order to get negative 6, by multiplying from negative 12, we have to multiply by negative 1/2. So I have to put a negative 1/2 here. And that's our equation. Okay, we could factor it out and make it in standard form, but factored form is fine here. So, when x values in a data are evenly spaced, the differences of consecutive y values are called finite differences. For example, some finite differences for the function y or f of x equals x squared are shown below. So, f of 1 is 1, because 1 squared is 1. F of 2, 2 squared is 4. 3 squared is 9. 4 squared is 16. Okay, so then we take this one, so f of 2, minus f of 1, 4 minus 1, and that gives us 3, which is our first finite difference here. Then we do 9 minus 4, we get 5. Then we do 16 minus 9, and we get 7. Okay, so this is our first order difference. Okay, now we want to get a constant value the whole time. So here we have 3, 5, and 7. We want to get the same number every time. So if we subtract these, we get 5 minus 3, which is 2. And if we subtract these, we get 7 minus 5, which is 2. So this is our second order differences. And since it is the same on the second order differences, we know that the degree of this equation here is 2. And if we look back at the original equation, it is in fact 2. So, the first 5 triangular numbers are shown below. A formula for the nth triangular number is f of n equals 1/2 times n squared plus n. Show that this function has constant second order differences. Okay, so the first one is 1. Okay, we can say that this 1 dot is a triangle. Doesn't really look like it, but we can say that. Then, if our second row is 2, then to make a triangle we have to add 1 more dot. So our second number is 3. Then if our bottom row is 3, we have to add a second row with 2 and a third row with 1. So our total number of dots is 6. And we have a row of 4 at the bottom. So our whole triangle is 10. And we're doing the first 5. So 1, 2, 3, 4. Now I have to do 5. So my bottom row is 5, my next row is 4, then 3, then 2, then 1. So total I have 15 dots. Okay, so now I'm going to do my differences. So 3 minus 1 is 2. 6 minus 3 is 3. 10 minus 6 is 4. 15 minus 10 is 5. So my first order differences are right here. So 2, 3, 4, 5. So they are not constant yet. So we are going to do another difference. So 3 minus 2 is 1. 4 minus 3 is 1. 5 minus 4 is 1. So my second order differences are constant. So I have shown that we have constant second order differences. Okay, so our property of finite differences with 2 properties. One is if a polynomial function f of x has degree n, then the nth order differences of function values for equally spaced x values are non-zero and constant. 2. Conversely, if the nth order differences of equally spaced data are non-zero and constant, then the data can be represented by a polynomial function of degree n. So if we have a degree of 2, we will get constant second order differences, and the constant will not be 0. And if our second order differences are a constant number that's not 0, then we can write our equation as an equation with a degree of 2. So the first 7 triangular pyramidal numbers are shown below. Find a polynomial function that gives the nth triangular pyramidal number. So we're going to begin by finding the finite differences. So 4 minus 1 is And then 10 minus 4 is 6. 20 minus 10 is 10. 35 minus 20 is 15. And then 56 minus 35 is 21. And the last one, 84 minus 56 is 28. Okay, so we have 3, 6, 10, 15, 21, and 28. Those are our first order differences. Okay. So now we move on. So we're going to find our second order differences. So 6 minus 3 is 3. 10 minus 6 is 4. 15 minus 10 is 5. 21 minus 15 is 6. And 28 minus 21 is 7. So we have 3, 4, 5, 6, and 7. And those are our second order differences. So we are not at a constant number yet, so we keep going. So we do 4 minus 3, which is 1. And we do 5 minus 4, which is 1. Then we do 6 minus 5, which is 1. And 7 minus 6, which is 1. So 1, 1, 1, 1. So that's our third order. Okay, so now we know that we're going to have a third order, or third degree polynomial. So y equals a n cubed plus b n squared plus c n plus d. So now we are going to plug in our numbers to a matrix. So because n here is going to be 1 for the first row, we are going to get 1 to the third, which is 1, so 1a, and 1 squared times b, so 1b, 1c, and 1d. And then our last column is going to be 1, because f of 1 equals 1. So our last column is going to be 1, 4, 10, and 20. Because we have 4 variables, a, b, c, and d, we are going to just have 4 rows. Then we put in 2. 2 to the third is 8. 2 squared is 4. 2 is 2. And then this d is just by itself, so it's 1. Then we are going to have, okay. So we know it's a third degree polynomial. And then we can substitute in for our function. So we get 1 equals 1a plus 1b plus 1c plus d. And then we plug in 2 and we get 4 equals 8a plus 4b plus 2c plus d. Now we're going to plug in 3. We're going to get 10, we know that. So 3 to the third is 27. 3 squared is 9. 3 stays 3. And then d stays by itself. And then the last one, we plug in 4. And we know we're going to get 20. 4 to the third is 64. 4 squared is 16. 4 and d is by itself. So now we can write that in a matrix. 1, 1, 1, 1, 1. Remember, this one goes at the end here. Then 8, 4, 2, 1 for the 4. Then 27, 9, 3, and 1 with a 10 at the end. And 64, 16, 4, 1, and 20 at the end. Okay, now we are going to go ahead and find the reduced row echelon form of this matrix. So we're going to put it into our calculators. Remember, we go to second matrix, then we go over to edit, and we're going to edit A. We need a 4 by 5, and then first row is all ones. Second row is 8, 4, 2, 1, 4. Third row is 27, 9, 3, 1, 10. And last row is 64, 16, 4, 1, and 20. So once we have those all typed in, we hit second quit. And then we go back to second matrix. We go over to math. And then we go all the way down to RREF. And then we go to second matrix again, and we pick the matrix that we put our values into, which on my calculator is A. And then we let the calculator do the math for us. I want to change it into a fraction. So then I get 1, 0, 0, 0, 1/6, and 0, 1, 0, 0, 1/2, 0, 0, 1, 0, 1/3, 0, 0, 0, 1, 0. So with these, we know that that's A, that's B, that's C, and that's D. So now we plug into our original equation. Which is here. So then we have y equals 1/6 n to the third plus 1/2 n squared plus 1/3 n plus 0. And if we want to leave this off, we can. Now, for example number 4, we are going to use our graphing calculator to find a polynomial function that fits the data. So, we are going to use the directions we have here on the back of our paper, and we're going to find a cubic regression. Okay? So, and the reason that we know it is cubic, let's do our finite differences. So 13 minus 5 is 8. 17 minus 13 is 4. 11 minus 17 is negative 6. 11 minus 11 is 0. And 56 minus 11 is 45. So that's our first order differences, and they're not all the same. So we go again. So we get 4 minus 8 is negative 4. Negative 6 minus 4 is negative 10. 0 minus negative 6 is 6. And 45 minus 0 is 45. So that's not constant. So go again. Negative 10 minus negative 4 equals negative 6. 6 minus negative 10 is 16. 45 minus 6 is 39. Okay, so if you notice, we're not really getting any closer here. And if we go the whole distance, we get 22 and 39 minus 16 is 23, and then we only have one number left. So, five might be it, but we doubt it. So, in this case, we are going to use a cubic regression. And the reason that we're going to use that one is going to become clear in a minute here. So we are going to clear our lists. And you go to your list by hitting Stat, and then Edit. And then we're going to type our X values into L1 and our Y values into L2. Okay, so now we have all of our numbers into L1 and L2. Now I'm going to go to Y equals, I'm going to clear my equation, and I'm going to turn on my plot, clear your equation, and then go up to plot and hit enter. And then I'm going to go to zoom stat, so 9. And it should show me my picture here. And it goes up and then down and then up again. So I know it's not going to be quadratic because it doesn't go like a U. So I'm going to use cubic because that's the closest that I can think of to that. So now I'm going to go back to stat, calculate, then cubic regression. Okay, remember our end behavior? If it starts down and goes up at the end, that means it has to be a odd degree. So it either has to be linear or cubic. If it was a W or an M, that means it's either quadratic or quartic. So we have to decide whether we're using an odd degree regression or an even degree regression. And in this case, we're using odd. So that's another reason we use cubic. Okay, so now we put all of our x values into L1, we put all of our y values into L2. So then we go down to calculate, and we get y equals, now we substitute our numbers here in for a, b, c, and d. So 2.713 x to the third minus 25.468 x squared plus 71.819 x minus 45.667. Okay, and that is our whole regression equation. So it's our polynomial function that fits the data. So to decide which one we use, if it looks like a line, we use linear regression. If it looks like a U or a mountain, we use quadratic. If it looks like a hill with a landing in it, then that's cubic. And then if it looks like a W or an M, then it's quartic regression. So those are our 4 types of regression that we have on here for polynomials. So those are how we pick which one we're going to use. Your homework's down here at the bottom.